Hello, everyone, and welcome to the first bite size of 2025. And we start with a really good one. With us today is Rob Syme from Sequera, and he is going to talk about content addressable data storage. And it's all yours.
Great, thanks all. Cool. Ooh, myself here. Let me just find Zoom again. Lost you all. Um, okay, great. I want to talk about the way we talk about data, which is a sort of odd and maybe confusing concept. It's one of the things I spend a lot of time thinking about. I have strong opinions about it, and people who see me at conferences I've like buttonholed them and talked to people about this for a long time. And you think that I would have spent a lot of time on the slides, given I spent a lot of time thinking about it. But of course, I left things to the last minute. But I hope things are clear. And basically, I want to, well, the purpose of this talk is for me to um, get these ideas out. People should tell me I'm wrong or I'm crazy, or what they think about it. So file paths are the worst, is the essential gist of this talk. I mean, if I was to be a little bit more kind, I could say file paths are for mutable data. But for us in Nextflow land, where we're dealing with runs, where everything's automated, and we don't necessarily want the outputs to change, we really are dealing with immutable data for the most part. File paths are the worst. So how do we refer to data? Like, for example, I have a path on a file system. We're so used to the idea of paths and file systems. We refer to data by its location on a system somewhere, like on a blob storage or an object storage or in a file system or in a URL. And we sort of have two options about how we construct that URL and how we refer to that data. Either we use option one, like you can see here, where we encode the metadata in the path implicitly. I mean, we're not really thinking about it as in term. I think when we write paths and make directories, we're not really thinking about encoding metadata, but that's sort of what we're doing implicitly. You end up with these long paths like this junky S3 path that I've got here, roblab and do not delete, RELECOV samples, and then maybe an ID that means something to someone. And maybe then there's some other text. Maybe there's a space in the file name or the directory name, and then maybe an ID paired, and then a file name. And so that's option one. You encode the metadata in the path. And that's interesting. And then option two is you encode the metadata somewhere else. You have like a nice, really terse path name. Like here, I've pulled a path from the SRA public bucket. Um, and you have some ID, like here, ERR1215609O. But that means something. But the only way to find out what that means is to look somewhere else. There's some other database. So option two is good for when you have lots of things of the same object and they're all the same sort of similar shape. Like SRA is a perfect example. There's like hundreds of thousands or millions of these FASTQ files or reads in some format. And so it's quite efficient to have this big database. Option two is pretty much a garbage fire and a disaster waiting to happen in a lot of different ways. But it's actually the sort of way that most of us work because most of us aren't dealing with like super regular file sort of shapes. So if we look at it a bit closer at option one, encoding metadata in the path, there's all sorts of ways in which this can go wrong. You might have multiple identifiers for pieces of data. How do you do that? Like, for example, here I have this SMD0081. What if I had another way of referring to that data? I have to choose one or the other. It can only be one in the path. It's hard to avoid redundancy. What if you have an identifier with a slash or a space? This whole sort of system breaks down. Um, Option two, this storing the metadata somewhere else, is a great plan in many cases, but you need more infrastructure. You need maybe a database somewhere like the National Library of Medicine obviously hosts a lot of the that does the heavy lifting here. again, it's great for those things like SRA where you have lots of the same type of things, but it's still complicated. You need to mint IDs. You need to make sure they don't clash. You need to have somebody needs to be the authority to tell you which IDs you can use. So there's all this extra stuff and extra infrastructure, which is why we don't often don't use it in day-to-day work. So that's somewhere else using storing the metadata somewhere else doesn't have to involve a database. So we, for example, might use the like excellent biocompute objects standard to write the metadata into a document. Here, I'm just like I have this output directory, and I'm going to use the great NFprov plugin, and I'm going to encode the metadata in some structured format and write it again as a files on a file system. Um, but this is complicated for a couple of reasons. Like, for example, if I use this counts file as input into another pipeline, I will, in that second downstream pipeline, have the metadata, I'll have another one of these BCO objects, which says the input was the file at this location, at this file location here. And then I'll have to implicitly know that if I was to find out how that file was generated, I have to go and then I have to go up two directories and I have to find that meta.bco.json and read that. So there's this sort of really difficult to define implicit connection. Um, and also, more importantly, it means that we cannot move any of this data. So as soon as you use one of these files as input into a downstream pipeline, we form this invisible and implicit connection between those two locations on a file system. And should we move either of those two directories, like the downstream output directory or this directory that's holding the inputs to the run, which are the outputs from a previous run, then we must either never move either of those data things, which is optimistic, or if we do move the data, we have to concede that the paths should be enough to define, like sort of understand what that data was. If we move the data and the data links break or the paths break, then all we're left with is the string that describes the path. And basically what we're saying is like, oh, you should sort of understand what that file was given this sort of loosely defined uh, directory structure. And I don't think that's very good. In contrast, metadata in Nextflow is fantastic. So here I'm just going to create a little sample sheet using the great NF schema plugin. So I have this really well-defined schema. I'm going to get a channel with these samples. Nextflow takes metadata seriously. And then I get a channel with some metadata and maybe some files. Maybe it looks something like this. Like here, you can imagine this is a channel and we have 3 items in the channel, and that each item in the channel has 3 elements, like a metadata object and 2 FASTQ files. In this simple example, I'm just using a map as the metadata object, but really we can do anything. We can have nested objects, we can have complex topologies, but let's just say we've got a simple map. And inside of the Nextflow pipeline, the metadata is treated in a really interesting way. The metadata and the files live in this lovely peaceful world side by side. The metadata and the files are sort of intrinsically linked as cognate items in this channel. I don't have to think about where the metadata is, where the file is. They sit together. They're treated sort of on equal terms. The metadata is treated as seriously as the data. And this is really great. It's really comfortable to use metadata in Nextflow. Like I have that meta object in all the NF core pipelines. I can meta.blah if I need to pull a piece out of that. It's always available, but I don't have to think about where it is in relation to the files. So basically, my experience of dealing with metadata and like describing data is in the file systems, we have these terrible long paths or complicated paths or paths that include identifiers that I have to go to some sort of external service to work out what they are. And then inside of Nextflow, everything is lovely and peaceful and chill. I have the metadata always available, ready to pull pieces out, and it flows through the graph with the objects. And then when the Nextflow run is finished, we write files back to the file system or back to object storage, and we're back to exactly where we started. So what I want is I want more of this middle part. I want more of dealing with Nextflow and dealing with metadata in the way that Nextflow deals with it. Is there a way where we can avoid one of those two options, encoding metadata in paths or um, relying on external services? And for that, I'm going to introduce two concepts, content addressing and IPLD. Now, I have a draft of a Nextflow plugin to do some of this. I'm not going to talk too much about that, but I just want to sort of introduce these concepts because this is important to understand where I'm going with that. The idea here, let's talk firstly about content addressing. The idea here is that you want to refer to data by what it is rather than where it is. So we're so used to thinking about paths as description of where the data is. But what if instead we refer to data by what it is? And the really simple way, and this is a bit of a gross simplification, but you could do something like this. I could take my FASTQ file, or maybe my genome.fa. I can calculate some hash of that file and then store it by its hash. So here I'm just going to move it into a directory in root blocks. It could be like, I'm just using that as an example. And then I would use that hash to define the location of that file. So when I run this Nextflow run, I'm saying Nextflow run dash dash input and then the file that matches this content. This gives me a couple of really great advantages. Firstly, you get lovely deduplication. I only store the file once. Like for example, in reference genomes, you might hash the file and then lots of different projects can use the same reference genome. They're all going to point because the genome.fa will hash the same contents and it'll be stored in the same location. But it means that I can communicate with other people a little bit more easily. If someone else reads this file and maybe this dash dash genome parameter points to a hash stressed file, they know which file I'm talking about. If they also have that file, they will also have the file stored with the same ID, the same hash. So if I get a project from a collaborator and I see that their parameters were dash dash input grch genome.fa, that doesn't tell me enough information about like, was it masked? Did it include decoys? All of the sort of small but important details and describing what a file is. Whereas if they use parameter with hash addressed files, I would know exactly what file. Like if, for example, if they use dash dash genome, some blocks, and then a hash, if I also had that file, I know exactly which file it is, and I know that we're talking about the same file. So that's content addressing. It's sort of simple and sort of uncontroversial. There are some important trade-offs. But the second part I want to talk about is slightly more complicated, and it's called IPLD. It's an existing standard. It stands for Interplanetary Linked Data, which is a grand term. And it's sort of like a weird alien concept when you first come across it. But actually, we use a very similar concept every day. And so I'm going to talk about IPLD, but first I'm going to talk about something that's very similar. So I've already described that file paths are the worst, except some paths are not. Some paths are magical. And an example of a magical path is this one, github.com/next/io/nextflow/blob, and then some hash and then makefile. So before I talk about IPLD, I'm going to talk about a little bit about how Git works because this path is magical. This path, where I follow it, gives me not only the information I like again with the services of GitHub of where to find this file, but it also describes the whole history of that file. It describes who edited it implicitly, who edited it, when they edited it, how the file has changed over time. So this one little hash not only describes the contents of the file, but the entire history of that file. So how does Git do this? Let's talk a little bit about Git. Git has this concept. I'm going to use a slightly simplified understanding or a sort of model of Git, but it's largely true. You can think about Git as describing these three major concepts: a commit, a tree, and a blob. So blobs are the file contents, the like literal bytes of the file. And you can see here I've represented these as these sort of blobs or blocks. And above those blocks is a little hash. I've just used short versions of these hashes. These are longer in practice. But just to simplify the slides, I've kept it to the first 6 characters. Um, so these blobs are hashed by Nextflow, by Git to produce these hashes. And then these hashes are used inside of the tree. So the tree is just this text, a number with some file, like describing the file, the permissions, and then a column which describes what type of thing this row is, and then a file name, and then a pointer, well, not a pointer, but like a hash, which refers to the hash of this file. There's another row in this tree. It's just you can think of it like a text file that has these 2 rows, some more numbers describing file permissions, description of what this file, this row describes. It's going to describe a blob, a file name, and then the hash, and that hash points to this blob. And then finally, we have commits. Commits point to parents and trees. So, and these are also hashed. So all of the elements in this sort of vocabulary are blobs or like some data, some bytes that end up being hashed. And those hashes are stored here. These hashes are notated here in green. And what happens is that Git stores all of these objects, all of the bytes describing the commits, the trees, and the blob in files and uses content addressing inside of there. So Git has a pretty rigid data model. Like for example, there's only one way of compressing the data. So it runs zlib on all of the bytes to produce these small objects, and it only uses SHA-1 to construct the hash. So it's quite limited and quite specific about how this protocol works. But that's okay. We're just using Git as an analogy here. So what happens behind the scenes? So let's take a real example. So we have this concept of commits in purple, trees in yellow, and blobs in blue. Let's say I run git add test.test, test.txt, and then I commit that. What we have is a commit, a blob, a tree, and a commit. And it creates 3 objects in .git/objects. So we end up with this directory with just a bunch of bytes. Those bytes are those zlib compressed trees, blobs, and commits. If I add another file and then run a second commit, we end up with more objects in this git/objects directory. So this is a sort of aggressive and sort of terrifying looking directory when you start. But because these blocks refer to other blocks in this graph, like I can reconstruct this graph about how it all relates to each other from these bytes and from this directory of blobs. What Git does very helpfully is it sort of renders these blobs. If I check out one of these commits, I pass it the name, the identifier of the commit, the hash, that unique identifier. Then Git can go into this directory. If I git checkout 8884, it looks for 8884. Here, these bytes here, it reads those bytes. And those bytes refer to these bytes. This refers to this block, which refers to this block, which refers to this block, or rather, it's just this block, which refers to this block, which refers to this block. This is the first commit. So just by having sort of the key, one of these hashes, I can reconstruct everything I need. If I git checkout a second commit, it refers to this block, which refers to this block, which refers to this block. Just one of these identifiers points to all the other blocks that I need in there. And Git will render out those blocks as these two files here, logs.txt and test.txt. Whereas if I git checkout 8884, it's just referring to this one blob, just test.txt. Then the other nice thing is that Git can render this DAG, this directed acyclic graph, in a number of different ways. It can render it as files on a file system, but you can also render it as a log. So there are different ways of sort of viewing this data. And really importantly, collaboration is super easy. Like, for example, if I have all of these Git objects, which describe the first two commits, so these 6 blobs, if I am collaborating with someone and they have some third commit, all they need to do is traverse down this DAG and work out what graphs and what sort of blobs or blocks this commit points to, which sort of implicitly points to all 9 of these blocks. And then I just need to copy out the missing blocks. So it's really easy for me to sort of work out what is missing. I look at the blocks that I have, the blocks that my collaborator has, and I just ask for the ones that I'm missing. And I just copy them into this directory. I don't have to think about where these blocks go because it's all content addressed. They can only go in the space by their hash. I don't have to think about that, and it's all self-describing. So all we need are blobs and these blocks and a starting point. So Git is great, but at best, it can only serve as inspiration for our Nextflow metadata problem, or our sort of computational problem, because it has a couple of limitations. But one of the things that it does really well, one of the things that Git does right, is it uses hashes that describe blocks that contain other hashes. And that's the really secret sauce. The fact that you hash these bytes, and inside of that, those hashed bytes are some text which points to another hash, which points to another hash, which points to another hash. And this property of hashes linking hashes is what gives Next that really magical path, its magical properties, that github.com/blob/hash path describe the make file and its entire history because of this property of hashes containing hashes. We can describe the entire history of a file or project with a single hash. The data is self-describing, deduplication comes for free. It's very simple to bring 2 users to a common state. The data is also conveniently auto-verifying. If someone gives me a block and says, this is the block that matches the hash you're looking for, I can just hash that block and confirm that it is indeed the data that I was looking for. One of the limitations, though, that Git can only describe blobs, trees, and commits. I'm only interested in, is there a way of extending this out to describe arbitrary metadata? Like, for example, metadata in files or Nextflow. For that, there's this existing standard called IPLD. It stands for, as I said before, interplanetary linked data. Basically, it provides primitives for building content address systems. It has this really simple data model. It can describe the following things: nulls, booleans, integers, floats, strings, bytes, list maps, and really importantly, links, which allows you to do this content address linking. And it also describes codecs, things like JSON, CBOR, and protobuf. The technical details of that we don't have to get into. But what is really important is this. This is basically what happens in IPLD. You can take some data, like here I have a meta map. It's just a key value store, or like a dictionary in Python parlance. This idea of you have keys and values, and I would turn those into bytes, serialize them in some form. Maybe that's serialized in DAG-JSON, so like a JSON-like object, or maybe it's serialized into protobuf or CBOR. The details of that are sort of immaterial. You end up with some bytes. And those bytes are the serialized form of that map. And we can hash those bytes IPLD uses a really clever system for constructing that hash, and that hash describes, or this is not a hash, this is actually a CID, content identifier, and this CID not only includes the hash, but it also includes information about which hash was used and also which serialization format was used, which means that, and so I get this CID, and then I store these bytes by this CID in some blocks directory. And here, this means that if I have this CID, I know exactly where to find the data. And I also know how to interpret that data because this CID includes information about the hash and the serialization format, so I can go backwards. So for example, actually, I'm going to skip this in the interest of time. And this can not only describe metadata, but can also describe files in the same way that Git can describe files in these hashed blocks. I could, for example, have here's a DAG JSON representation of a directory containing two files. We have this concept of links. And here, this link is this little block contains the text of a hash of another block. So the hash of the block describing this chromosome 1.faster or the counts.csv, which gives me a new CID, a new fingerprint, or a new identifier for this block. And this block implicitly contains hashes or pointers to other hashes. And I end up storing this in some block store. And this can be anywhere. Maybe it's on a file system. Maybe it's on object storage. And this top level CID implicitly describes all of the pieces underneath it. So how does this relate to Nextflow? Well, there are a couple of options here. A couple of opportunities. We can use CIDs to describe workflow inputs. Maybe we can use CIDs to describe workflow intermediates. And what I really want to do is get to the point where you can use CIDs to describe workflow outputs. So to describe an inputs, you might, for example, have a CID which describes a directory containing a bunch of reference data. And I have this channel.from CID function, which will take a CID and optionally pathing into that block. And that CID describes the sort of references at a particular point. The nice thing about this is that if I have some blocks on my local file system and maybe NGI iGenomes has some blocks, you can see here the blocks that I have, QP, QM, BPG, are a subset of the blocks on NGI iGenomes. So if I were to take this, maybe I have a workflow that has this line in here, channel.from CID, and then a long hash slash human genomes.faster. The plugin would look first here at the blocks that I have in my local store. Maybe this is my preferred way of pulling data. But if I see that I don't have this block, it'll then overflow to a second block store or a third block store. These are really composable. And okay, so it looks like NGI iGenomes has this block, QMPEH, QMPEH. Great. So NGI iGenomes has the block, and then I pull down the blocks that links to. It links to QPMG and QMRPY. I know, like when I decode this, I can see that /human/genome.faster is in this block, but I already have these ones, so I know that I don't have to pull them down. I only had to pull down the one block that I was missing here, and then the human genome.faster is contained in one of these subdirectories. I don't have to think about how to arrange that data into folders, and I can compose data sources, both my own and external data sources together. You can use CIDs to describe workflow intermediates. I'm going to skip that for the moment. But what's really interesting is when we can use CIDs to describe workflow outputs. Provenance tracking is really hard. But what if we could conduct the Nextflow run, and it gives me some top-level hash that describes the run. It has all of the metadata describing the inputs, the outputs, the containers, everything I need to describe the run, as this hash, and then the outputs could be that hash slash sample slash counts.tsv, which means that in a downstream run, if I was to use this as input, this sort of path is now magical. It has that magical property that I described in Git, where the hash here describes the entire history of that project, not just like a place on a location on a file system, but the entire history of that project, which means that I have provenance all the way back through. So if I see a run that uses this as input, I can go back and grab the blocks for that run and understand how that run was created. And if that run used inputs that were also hash addressed, I could step back all the way through time and see the entire history of the project and all the files. There's a lot more to cover, but I'm going to pause it there in the interest of time. I'm just going to double check if there are questions.
There is one question by Madi.
Yeah, so Muddy says, thanks, Rob. It seems the part of the concept described addressed the same concerns that the open source project like Delta Lake, Apache Iceberg, and Project Nessie are also working on. I'm really curious about the differences in this feature in Nextflow compared to those projects. Is there any overlap? Yes, it's sort of a complicated question. I would prefer a simpler open standard to that sort of data lakehouse platforms. But it's a good question, and maybe we can talk offline about that.
So I guess we are now in the question phase. Thank you very much for your talk. I allow everyone now to unmute themselves. So if you have any questions, please unmute yourself and ask your questions directly.
Hello, Rob. Thank you for your excellent talk. I'm a bit sad that you cut out some parts in the interest of time because they were really intriguing. But I wonder, have you heard of DVC, data version control, and how does that relate to your ideas?
Yeah, DVC is great and introduces a lot of the important concepts. Like it does the content addressing part really well. What it's missing is the open and flexible and sort of agnostic metadata encoding standards that IPLD give you. But yes, DVC is awesome. And if you use DVC, like you already get sort of half of the way here. Like half of those concepts will be really familiar. The idea that you hash at the files and store the files by the hash, which is exactly what DVC does. What DVC is missing is the this idea that like we should treat metadata and data in exactly the same way. Like metadata is just as important as data. Like if you have a file with some bytes in it, that's useless unless you have the accompanying history of the file and understanding about the patient ID, the cohort, all of that sort of stuff. It's just as important. And so what I would like is a system that treats these metadata objects on equal footing with the data objects. So if it all is just blocks, hash address blocks, then like there's this lovely seamless movement between data and metadata.
I think the goal is fantastic. I just wonder, I think that it sounds a bit like a Herculean task because as soon as you kind of modify the metadata, let it just be the capitalization of the patient name or something, you end up with a different hash, and then maybe your whole content addressing also breaks down at some point.
Yes, it's a good point. So there are some important trade-offs here. This is not some perfect system. The modification of patient data, like if you have some top-level hash which is like the Merkle root for some like large tree, you can imagine having some update operations which just traverse the tree and then like because the blocks, the metadata blocks are really small and they're separate from the real data blocks. You can update. So let's say you have the Merkle root for a large tree and then there's some patient ID you want to update. You only have to update the branches between the root and the patient you want to update. You don't have to update the rest of the tree. You just have to update those branches, which is not a huge thing. And then you get a new top level hash. And all of the other data that has remained unchanged can still be blocks in your block store. You only have to update those paths in between. You get a new Merkle root which describes all of your projects. It's not an impossible situation to update that. You just need you just need clever ways of knowing how to update those blocks. And most of it is just rehashing two hashes. Like there's one important update where you actually change the metadata, and then everything else is just rehashing the blocks, which is pretty quick.
Sounds like you're gonna to found your own startup in the blockchain metadata tracking business.
We're not doing blockchain. This is not one of those. I'm very happy it's secure. This is not a moneymaker. Like the interesting thing about this is that, okay, so one of the big trade-offs is that one of the really big trade-offs you have to make if you were to take one of these approaches is you have to let go of the idea of having files in file systems that you can easily navigate. Like it's so comfortable and so safe to have like human readable, like these directories which we navigate. So you need to have a system which renders these blocks. And like Git does it really lovely. We're all very happy using Git, even though under the hood, because we have this system for rendering those blocks in different shapes as graphs and Git log, or in file systems with Git commit, or in any number of other ways you can render them. So what we need is really sensible and really robust ways of rendering these graphs. And then I think that's what's required to have people move away from them. Or like let go of files. The other really important thing is that the benefits of these approaches scale really well. So it means that like if you and I, Matthias, are able to work seamlessly without collaborating, like without communicating, like for example, we can do these block store things. You don't have to care about how I stored files. So it requires a sort of community adoption, well, not requires, but it is most helpful when there's a large community adoption. One of the interesting positions that we find ourselves in now is that Nextflow has this large community adoption, and certainly I'm not saying that Nextflow will force this on anyone. But if Nextflow provides it as an option, or if like via a Nextflow plugin, for example, and people start to adopt it and people see the value in it, then we can sort of get this get the required steam and sort of motivation or movement.
Yeah, may I actually ask something there? So, I mean, the whole thing just kind of stays and falls with the adoption, as you say. So, if just anyone in the chain suddenly decides they don't want to do this because of, I don't know, time, convenience, who knows what, then it kind of falls apart, right? So, how would you ever get everyone to do it without fail?
Yeah, so I'm using it at the moment for like small internal projects and like but if even if someone in the middle breaks the chain, we're no worse than we are now. Like for example, at the moment, like if I inherit data from a collaborator, I have no idea how that data was generated. Like they give me some files. Like it's an absolute disaster at the moment. Like it is really hard to step back through time. So even if we break the chain, we're not in any worse position than we are at the moment. That would be my argument.
Okay. Thank you so much. Is there any more questions from the audience?
So I have a small question. I mean, this entire idea of using these hashes and blobs to be able to look through the entire tree also kind of requires the person you're sending your pipeline to, that they're now picking it up, that they have access to this entire tree as well, right? Which would then imply that you have some kind of shared Git repository with all these reference genomes or something that they can actually Git pull from. Which would presumably also then extend to the data itself, like the raw data that you're using, which in many cases, whether you're working medical or even in ancient DNA, wouldn't want to openly share and put into a Git repository, right? Is there a way around this? Is there some kind of like way that you can share data in this kind of format without needing to actually worry about the data getting out?
Great question. Great question. And so yes, the way you would do that is you don't necessarily have to share all the blocks. You can imagine you've got these leaf nodes which describe like the bytes of the files, and then all of the rest of the nodes are the nodes describing how the graph is constructed. You don't you would perhaps not share the leaf nodes and make the other nodes available. So you get to choose which blocks you share. And you know what each block represents because they're self-describing. So you could, for example, maybe just share part of the graph and keep everything else private. So you get to just, in the same way that you would have rules around which files you share, you would have rules around which parts of the graph you share.
So I hope this answered your question. Phil.
Hello.
Yeah,
We've discussed this quite a bit in the past, and apologies if I missed this in your main talk. But what about IPFS? The file system already exists based on much of this technology. Is there any way that we could sort of interface with this, even if we don't leverage that technology as is? Is there any way we could sort of tie into that as an open standard so that other people on existing systems could find adoption easier?
Yeah, good question. I didn't cover it. So IPFS is built on top of IPLD. So IPLD is this really abstract data model with those nulls and maps and arrays and integers and stuff like that. So it's super, super simple. And so IPFS is just a standard which says like objects of this shape, like with this, like maps with these keys, we're going to call those files, and we're going to make standards like tooling to represent those as files, or render them as files in the file system, much like Git does, takes those abstract blocks and turns them into files in the file system. So yes, if we were to use, we could use the IPFS standards, and that would give us a whole bunch of tooling that we can inherit. But we go like extend beyond that because we want to represent more than just files. We want to also include that metadata. So we use IPFS standards for the files and just like raw IPLD for the metadata. And
is it possible to do that in such a way that the IPFS systems basically just ignore all the stuff it doesn't recognize?
Good question. I'm not 100% sure. Yeah, it's a good question. Like, how do you have them sit side by side? Yeah, I'm not sure. There were some other standards like the Web Native File System, which was another sort of file system-y thing based on IPLD. But that fission company folded, so I wouldn't want to build on it. Whereas IPFS is going to be around for a long time.
It'd be very nice if we could have IPFS for all the files, and then if you're using our tooling, you get the value added stuff of being able to also trace the metadata. But if you're just using vanilla IPFS, you can just access the data through regular POSIX file systems.
The other really big trade-off with IPFS, or another important trade-off with IPFS, is by default it's designed for peer-to-peer file sharing. So what they do is they take large files and they break into small pieces, and then break those small pieces, and you get a Merkle tree which describes the file. So, which is good because if you're doing like peer-to-peer transfers, it means you only ever like sending small chunks that are quickly verifiable, which means that like reduces the power of bad actors in a system by like, can you imagine like a bad actor in a peer-to-peer system sending junk blocks? If it was a large file, you'd have to download the whole file before you could hash it and discover that the person sent you a garbage block. Like the whole peer-to-peer thing, I don't think we're interested in our world. We're already used to shared file systems and shared object stores. We don't have to think about peer-to-peer. But the IPFS protocol for their block swapping does chunk these things into 2 meg blocks, whereas we probably would prefer, I think in most cases, and this is something about which reasonable people might disagree, we would probably prefer to just keep them as large files and just hash them, because that gives us the advantage that if we do want to just like take that file and move it to like a non-IPLD system, we already have it. Like it's a file and object store and a file and file system in its complete form rather than broken up into pieces. That's the thing I'm really struggling with at the moment. It's like, do we totally abandon IPFSs, like using IPFSs peer-to-peer stuff for the sake of keeping files intact?
Yeah, I can imagine us exhausting inode counts quite quickly if we're having many terabytes or petabytes of data chunked into 2 megabytes. That'd be a lot of files.
It's a lot of files, yeah. And then if you're using object store, there you have GET requests, API requests for each of those chunks. It's not a lot, like a terabyte. I think I calculated an extra 20 cents to pull just in the API calls. But it's like the thing that I've learned at Cyxtera is that whatever you think a large amount of data is and what an extreme amount of data is, there's always someone who's doing something 10x of what you expect. So yeah, I want to be very careful about that. So I think we'd probably end up blocking, or you do something like there are objects which describe lots of hashes together, and you can bomb together in the index and stuff like that. So there are ways around it. It's just haven't quite settled on a really neat solution.
Thank you, Rob.
I have a
we're quite
question.
over time. Yes.
Rob, I'm curious about how we can manage data lineage. I know, for example, when we want to work with tabular data, we can use maybe open lineage, but what about Nextflow case?
Yeah. So this is all with the view that to control and sort of make visible the lineage of data. We can use Nextflow, like a Nextflow plugin or even Nextflow in core to write these objects which describe the properties of the run, like the outputs, the inputs. Like Nextflow run knows its own versions, it knows its own containers. So we can encode all of that into metadata which describes the run and hash that. And so that would be that could be the block. Or we
will be able to
standards.
visualize relation between the data and having visualized lineage.
Yeah, the first thing is the visualization of the lineage can come after. My approach would be the first thing is to encode it in a way that like actually just save that information rather than throwing it away. And then we can work out ways of visualizing on top of that afterwards.
Oh, perfect. Thanks.
Yeah. First thing, have the data to visualize, and then we can build all sorts of fun stuff on top of that. But we need to have the data about how these things were constructed first. Ooh, I haven't seen that. I haven't seen that Marquez project. Oh, that's the open lineage originally. Yeah, no, I have seen that. Yeah.
Yeah, as I wanted to say, we're quite over time. So if you have any more questions, I'm sure Rob is more than happy to discuss that with you on Slack, maybe. But I would like to thank you again for taking your time and introducing at least me to this subject. And everyone who stuck around until now for listening in, but of course, also the ones who left a bit earlier. And I hope to see you all for the next Bite Size talk. So thank you very much.
Thank you all so much.